Most people have seen a drone. Almost nobody has ever seen how one is truly made. Until now. Before the first cut is made, before the first mold is filled, the journey begins here. Raw materials. Every shipment that arrives at this facility undergoes a gauntlet of verification before it is even allowed near the production floor. The materials wait here in climate-controlled darkness, their metallurgical properties preserved, their chain of custody unbroken. The digital twin of the factory allows production planners to orchestrate every movement, every cut, every assembly step before a single machine is powered on. The physical and the digital move as one. Autonomous vehicles and robotic handlers move materials through this facility without human touch, reducing contamination risk and ensuring that every billet, every roll of prepreg, the first cut. What was a raw billet becomes a component. The machine does not hurry, but it does not stop. 5 flutes, 12,000 revolutions per minute. Each pass removes precisely 0.8 of a millimeter of material. The bulkhead emerges. 60% of the original billet is now chips on the conveyor. What remains is a structure. 147 dimensions, every one checked, every one recorded. The digital traveler grows thicker with each inspection. The machines can remove 99% of the material, but the final 1%, the feel, the touch, the judgment of a trained hand.
The wing skin begins as 97 individual plies of carbon fiber prepreg, each one precisely oriented, each one a specific shape.
Laser projectors guide every ply position to within 0.5 millimeters of the engineering specification, but it is the technician's hands that feel the material. Embedded within the carbon fiber, a network of fiber optic sensors will monitor this wing for stress, for strain, for damage. For the next 8 hours, the laminate will be subjected to heat and pressure that mimics the conditions at the bottom of a deep ocean. The resin will flow. The autoclave has done its work. 97 plies are now won. The wing skin is born and it will carry this aircraft tigged. The robot trims and drills with a precision measured in microns. There is no hesitation, no second guessing. The ultrasonic pulse travels through the carbon fiber at 6,000 meters per second. What it sees, no human eye can see. The wing skin and the fuselage bulkhead were born in different worlds, but they will meet here in subassembly and become one structure.
Every fastener in this airframe is installed to a documented torque, every single one. There are over 4,000 fasteners.
The wing is structurally complete. 4,000 fasteners, 12 ribs, 2 spars. The beam is the body, but the airframe is the body, but the avionics are the brain. Every flight computer, every sensor processor, the turbine spins at over 1,500 revolutions per second. At that speed, the tiniest imbalance would tear the engine apart. The landing gear is the first part of the aircraft to touch the runway and the last to leave it. Its design must absorb the energy of a controlled crash. The kit is complete. The wing, the engine, the avionics, and the landing gear are now gathered in one place, waiting for the moment they become one aircraft. The turret is the drone's eye. It sees invisible light, in infrared, in laser designator wavelengths, and it surges. The coating is not just color. It is a multi-layer system designed to absorb and scatter radar energy. 178 microns, not 175, not 180. The coating thickness at every point on this airframe is Julus. The laser does not sand. It does not grind. It vaporizes the coating molecule by molecule, leaving the underlying carbon.
The robot lays the coating down. The laser removes it where needed, but the final touch, the
surface treatment is complete. When these components are assembled, their surfaces will perform multiple functions: aerodynamic, electromagnetic. The laser tracker measures every critical point on this wing against the digital twin. 50 microns across 40 feet.
24 holes. Each one must mate with its counterpart on the fuselage within the width of a human hair. If even one is out of position, the wing will not bolt on. Inside the fuselage, where no eye will ever look again after final assembly, the laser tracker sees everything.
The data is collected. The measurements are complete. But the decision, the final authority to say this component is all components accepted, proceed to integration. The stamp is a mark of acceptance that will outlast every digital record.
Integration. The moment when components become an aircraft. Every piece, every fastener, every
Contact.
The mate. The moment the wing and fuselage become one. 4 years of design, hundreds.
The nose section carry the aircraft's eyes. As it mates to the fuselage, the sensor turret that was within. The V-tail gives this aircraft pitch and yaw authority through just 2 moving surfaces, reducing weight. The landing gear will carry the aircraft on the ground. The engine will carry it through the sky. Both are installed within hours of each other. The aircraft is complete. Now it must prove it works. Every system, every sensor, every movement.
The control surfaces are the aircraft's hands. They must move precisely, respond instantly, and never fail.
Ignition. The engine that was balanced to a fraction of a gram now spin 100 revolution
Unit rates. The turret sees what the pilot would see if the pilot were on board. But it sees more, in infrared, in laser designation.
Integrated systems test, complete. The aircraft has proven it can fly, navigate, sense, and communicate.
The final inspection, the last set of eyes before this aircraft leaves the factory. These inspectors carry no responsibility for building it.
This is what a $54 billion investment in manufacturing capability looks like. This factory builds certainty.
The signatures are applied. The digital record is sealed. This aircraft has been built, inspected, and tested to a standard that no commercial product ever reaches.
The aircraft leaves the manufacturing floor. It will never return here. From this point on, its life will be measured in flight hours, not build hours.
The packaging is not an afterthought. It is the final manufacturing step, designed to ensure that every hour of labor. The container is climate-controlled, shock-isolated, and satellite-monitored. From the moment those doors close, the factory will know.
The shipping documents transfer custody from the factory to the carrier. For the duration of the journey, the container's environmental monitor will contain.
With that final entry, the manufacturing record is closed. 500 pages of data, thousands of measurements.
The aircraft leaves the factory. It will be reassembled, flight tested, and deployed to a location that may be anywhere on Earth.
The factory's work is proven here, not on the test stand, not in the inspection bay, but in the sky where the aircraft was always meant to be.
This is what it takes. 12 steps.